Thanks, Arunas. I'd like to start by acknowledging my co-authors at the USGS Great Lakes Science Center, Ed Roseman, Kevin Keeler, and Tim O'Brien. So bloater are the sole remaining species of historically diverse native clade of deepwater ciscos that supported commercial fisheries and native piscivore diets before populations collapsed in the mid-1960s, mostly attributable to commercial fishing. As I just showed, since 2005, bloater have exhibited multiple strong year classes and are now the most abundant non-goby offshore prey fish in Lake Huron following a collapse of alewife between 2003 and 2004 and drastic declines in rainbow smelt. So after the bloater populations in Lake Huron collapsed in the mid-1960s, they remained at all-time low abundances and then resurged really well and supported a commercial fishery again from 1980 to 1999. Since then, commercial catches declined sharply, and they've basically been non-existent from the commercial fishery through the present. But since 2008, there has been a recovery of adult bloater abundances, so much so that they actually are, since 2008, have been at or above the abundances that supported the resurgence of the commercial fishery from 1980 to 1999. So the dashed line on the bottom figure represents the average annual abundance of adult bloater from 1980 to 1999, and you can see that since 2008, densities of adult bloater have been at that level. But over the course of the trawl survey that the USGS has conducted, there's been changes in the length frequency distribution, large changes. Beginning in the early part of the time series, the darker colors are the proportion of the lake-wide trawl catch that fall within each of these different size categories, and darker shades representing larger fish. You can see that in the late 1970s, 20 to 30% of bloater were at sizes 270 millimeters up to 400 millimeters. Commercially marketable bloater are usually regarded as being at 229 millimeters or greater. Moving forward, from 1990 to 2004 represents a period of near zero recruitment of bloater. So the bloater that grew really well and had intermediate recruitment from the 1970s and 1980s survived and grew to large sizes that supported that commercial fishery that was basically dominated by older, larger bloater. But then populations approached all-time lows again in the early 2000s. And you can see that even though we've had strong recruitment events since 2005, there really hasn't been a recovery of bloater of large sizes, prompting the research question. So the thing to take home here is there's been a large contraction of the length frequency distribution since the late 1990s. So the first thing I want to do with this presentation is examine the role that changes in growth may be contributing to low abundances of large, commercially valuable bloater. Two immediate things to consider: acknowledging good recruitment, but then not seeing large bloater might be changes in growth or mortality. But we know from recent studies have shown that bloater don't comprise a very high percentage of piscivore diets in Lake Huron, leaving growth as maybe the most likely thing to look at first. Also with this presentation, I'll present information on the spatial patterns in the population dynamics of young of year and yearling and older bloater, both with respect to depth, use, and geographic distribution. So Ed kind of went over how the survey works. All of my presentation is on individual data from the bottom trawl survey. Since 1973, 5 U.S. ports have been sampled, and then since 1999, Goderich, Ontario has been sampled. I have individual data on total length, weight, and ages from scales. There's a primary data gap from 2005 to 2011 where scale ages were not collected on bloater, and then again in 2013 they were not. So I fit length at age and weight length models to year classes that existed from 1973 to 2004, and then compare those to our observed estimates from 2012 and 2014. To do this analysis, I used time-varying growth models. So for length at age, we used the standard von Bertalanffy length at age model, where estimated length for cohort C and age A is a function of a cohort-specific asymptotic length, the L infinity, and then a cohort-specific Brody growth coefficient parameter, Kc. And then for looking at weight-length relations, I used a log transform standard allometric growth model, where the log estimated weight was region and year specific and was a linear function of log A, which is a region and year specific intercept, and B, which is a region and year specific slope parameter. To make these models time varying, I allowed the growth parameters to follow random walk process that takes advantage of the interrelatedness between years or year classes, but doesn't specify an underlying mechanism. A random walk process simply states that the value of a parameter in time step t is equal to the value of that parameter in the previous time step plus a perturbation drawn from a normal distribution. So getting to the results, the plots on the left are length in millimeters of fish at ages 7 and 8 in the top figure, 4, 5, and 6 in the middle figure, and 1, 2, and 3 in the bottom figure. And then the line represents the estimated values, and the numerals represent the observed mean values. See, overall, the model predicts the observed values pretty well, and for the larger ages, we see large declines throughout the time series. For ages 7 and 8, there have been 24% decreases in estimated length at age from the 1973 year class to those ages in 2004. Ages 4 through 6 had similarly large declines. And then ages 1 through 3 showed a 14 to 16% decreases in estimated length at age through 2004. But there was a period of increase, especially for ages 1 and 2 and 3, that corresponds to that low recruitment period. So there may be some evidence of density-dependent effects on the smallest, youngest fish. But overall, there's been declines that have that those increases in growth in the younger years haven't translated into increases in growth in the older ages. And you can see that in 2012 and 2014, the observed mean lengths at age indicated by those numerals were lower than the whole time series through 2004, indicating continued declines. So looking specifically at the dynamics of the parameters, we see an overall negative relationship between the asymptotic length that fish achieve at older age and the rate at which they approach it. But there might be some differences in that relationship. You can see early in the time series through 1990, the rate at which fish approached their asymptotic length remained about the same, despite continued declines in the asymptotic length, beginning with the beginning of the survey, which suggests that even perhaps the start of the survey, growth in Lake Huron was declining. And we see a really sharp decrease in the asymptotic length beginning around 1990. That also corresponds with the really quick increase in the rate at which those fish were approaching asymptotic length. And again, that may be related to density-dependent effects. And then we see through the 2004 year class, there was some small recovery in asymptotic length, but there's also been a decrease in the rate at which the fish approach it. Looking at this relationship, we have a paper under review that explains kind of our thoughts behind this a little bit more, but we think the changes in growth may be most related to changes in the lower food web, dipriya abundance, and the underlying productivity of the system. So breaking the time series into 3 periods, from 1976 to 1990 represents a period of intermediate recruitment of bloater, but it was the time of highest productivity in the lake during this survey. And at this time, see, asymptotic lengths were high ranging from 320 millimeters up to close to 400 millimeters, and the rate at which the fish approached it was pretty low. Then beginning in 1990, I'm talking about the bottom figure here, you see these quick decreases in the asymptotic length and sharp increases in the rate at which the fish approached it. And then there's kind of a shifting of the relationship of those two parameters beginning in the late 1990s, corresponding with the period of lowest productivity in the time series and variable high recruitment. Now getting into the changes in weight length relations, see overall similar declines, especially among fish of the largest sizes. So on the figures on the left, we've got estimated weights at 3 different lengths, and then each of the different symbols corresponds to different regions of the lake. Weights of 250 millimeter bloater declined about 17% through the mid-2000s, and there were gradual declines in 200 millimeter bloater as well. In 2012, no bloater greater than 232 millimeters were observed, or in 2012 and 2014, and you can see that by the absence of those points in the top figure. Overall, among all regions, similar trends have been seen, although there is some evidence that bloater in the north region weighed less in the late 1990s to the mid-2000s. So there's been large declines in bloater length at age. 14 to 24% declines in ages 4 through 8 from 1973 to 2004, and then our observed mean lengths at age were at all-time lows in 2012 and 2014 across all ages. And there's also been decreases in body and condition as indicated by decreases in estimated weights at those lengths. So this has implications for a common behavior that bloater exhibit, which are diel vertical migrations. Bloater that are lower in body condition tend to be lower in lipids and undergo greater pressure changes or buoyancy changes when performing diel vertical migrations. So there could be this positive feedback loop where now bloater are lower in lipids and then have to exert more energy to move up and down in the water column, and that may be playing into these decreases that we're seeing. Alternatively, I know Bo Bonnell and Chuck Medengen have hypothesized for Lake Michigan that bloater aren't orienting to the bottom as much as they used to, perhaps in response to declines in diapauria, and this affects both maybe our ability to sample them with the bottom trawl, but also maybe a compensating effect for having lower lipid levels and there not being diapauria. Regardless, all of these have implications on the value of bloater as forage, both where they are located in the lake and the value of them calorically. But we think these results show that the decreases in bloater growth are most implicated in the low abundances of large bloater in Lake Huron. In recent years, the age structure has been pretty well balanced and older ages well represented. So what I have here is a figure by year on the x-axis and the proportion of the lake-wide catch that falls within each of these ages. So darker ages or darker colors representing older ages. You can see in 2012 and 2014 there's pretty even distribution of ages 3 up to 6 or 7, which suggests that mortality or predation on bloater is pretty low, and this is in line with the diet studies that have looked into this. Overall, we think this shows that bloater of the 2008 and subsequent year classes would have to follow growth trajectories unlike those characterizing the 1973 to 2003 year classes that we modeled in order to reach marketable size and appreciable abundances. So that was the growth part of the presentation, and now we'll look at kind of the geographic dynamics of bloater. So that each of these figures shows the density of young of year, which are the dots, and yearling and older, which are the lines. In the 2 northern ports, Detour and Hammond Bay on top, the central ports that are sampled, Alpena and Au Sable Point in the middle figures, and Harbor Beach and Goderich, Ontario, the 2 bottom figures. Things I want to point out here are that the higher abundances seen in the early part of the time series that really contributed to that resurgence of the commercial fishery appear to be driven by northern main basin of Lake Huron. So we have these intermediate recruitments events in the early 1980s that led to highest yearling and older abundances in the early part of the time series. And then throughout the lake, there was the decreases in abundance. And then since 2005, where we've had these pretty successful recruitment events that have mostly occurred in or have been captured by the trawl in the southern ports, Harbor Beach and Goderich. And I want you to especially notice that the y-axis is different, as at a different scale for Goderich, Ontario. So we see these high recruitment events in the two southern ports, but it looks like these recruitment events have translated to increases in abundance of yearling and older bloater throughout the rest of the lake. So you see kind of increases in the blue line in the central and northern ports. There's also been changes in the depth distribution of bloater over time. So with this figure, the top is depth distributions of young of year bloater, and the bottom is yearling and older. The darker colors representing deeper depths. One other thing I want to point out with the top figure is that young of year bloater tend to be more distributed throughout more of the depths than yearling and older, which tend to almost exclusively be caught in that 50 to 90 meter depth range. But you can also see that there's been a shift of young of year bloater out of the 0 to 30 meter depth zone and into more of the 30 to 90 meter depth zones later in the time series that corresponds with changes in recruitment from the northern ports to more southern ports more recently. And there's been overall declines in the mean depths of capture throughout the main basin of Lake Huron over the entire time series. There's a Stephen Riley paper that describes this pattern through the mid-2000s, and this has continued through the present. That's all I have to present today. Thanks for your attention. Try to take any questions.